My name is Taylor Leach, and this is Physics 2211 Lab 4 Oscillations. So, the purpose of this experiment is to predict the motion of an oscillating mass using observations from tracker and creating a computational model that replicates this motion. Analyze the different types of energies of the system, such as kinetic, gravitational, and elastic energy. The system is the oscillating mass, and the surrounding includes the spring and the earth. However, for energy calculations, the system will include the oscillating mass, spring, and earth. So the key concepts that we need to know are the energy principle, that delta E of the system equals the work of surroundings plus Q. Um, we also need to know delta K plus the delta UG plus delta US equals 0 because the system is the block and then the spring and the earth, which all act. And because there's no work being done, this means that energy is conserved and they all add to 0. So kinetic energy is 1/2 mv squared. Spring potential energy is 1/2 kinetic energy, or the spring constant, times the length of the spring. And then the change of gravitational potential energy is mg delta y. So in our tracker observations, we inputted the x and y values into tracker for the conservation into the video file that was later used in GlowScript. Motion begins in frame 5, and we included a picture of the calibration, as well as a picture of the table that took the data of the oscillation. So our computational model used the same mass, as well as the starting positions that we found from tracker. We calculated the spring constant by using the data received in tracker to determine the change in energy and the force of the spring and the potential energy of the spring that led to us finding the spring constant. We also used the relaxed length of the spring from tracker. We defined our initial energies just using the first energies, and then as they change, we updated them. The force of gravity was just the ball's mass times g. Force of spring was the spring constant times the spring length times the direction. And then the F net was those two forces combined. The ball's velocity was updated due to F net over m delta t, which is the velocity update formula. And the position was updated with position over velocity, or position plus velocity over time. The spring length was updated in accordance to the ball position and the spring position. And then using all of this information, we were able to calculate the changes in the energy by plugging the values that we found into the energy formulas. So in our results, we found a small discrepancy between the model and the actual position, which could be contributed to many things such as air resistance, drag, and other external forces that were not included in the model, giving this slight discrepancy. So what does it mean? We realized that this stayed true to the conservation of energy formula because the delta E was always equal to 0. Since all of the forces were in the system and work was not being done, this means that energy was conserved. And we know energy was conserved because there was no work or change in thermal energy. The gravity present in the x direction versus the y direction caused a difference due to the fact that it was an additional force, making for faster oscillations since there is more force acting on the spring.